Welcome back, students, to Rama Teaches You. Today we are going to do IB Physics theme D, electric field, right? Electric field, electric and magnetic field. Okay, we have already made one video on this. Okay, today we are going to start with the second part of the chapter, that is electric fields. We are going to focus on how these fields give these forces the ability to exert themselves. How these fields give the forces the ability to exert themselves without having physical contact between them and the particle. Okay, so in electric fields, in topic D1, the concept of gravitational field was developed, and you were introduced to the new concepts such as potential and electric fields. Now, in field theory, all forces of the same type, in our case, the inverse square forces, can be described using similar concepts. So we have already discussed what an inverse square force is, right? A force whose magnitude decreases as the distance between it and the object increases by the inverse of the distance between them. By inverse of the distance between them. Topic D1 gives a good understanding of gravitational fields, but also the concept and are reintroduced here as it gives a different perspective of the field. Now, we know that the gravitational field is always attractive. If I place an object like this, it is always going to fall downwards. There is no repulsive force in gravity. Gravity is always an attractive force, right? It is always an attractive force. If I keep on dropping like this, what is going to happen? The spen is never going to repel the Earth's gravity because Earth is under negative potential. Okay, so basically, an object always goes from a higher potential to a lower potential simultaneously. Like, what do you call it? Not simultaneously. Naturally, naturally, right? Okay, it will never go away from the Earth. It will never go away from the Earth because the gravitational force between two objects can never be repulsive. It can only be attractive in nature. Okay, so we have to reintroduce these concepts for electric as well as magnetic field, because in electric and magnetic field, when like charges are placed next to each other, or when like poles are placed next to each other, in the case of magnetic fields, you get to see what? You get to see a repulsion. Understood? You get to see a repulsion. So let's start the class. Okay, what is the first thing? Electric field strength. Okay, before that, there is, I think, a small topic we have to understand. There are many similarities and differences between fields. For example, the gravitational fields are always attractive, whereas electric and magnetic fields can be attractive as well as repulsive. The gravitational potential are always negative, whereas the electric and magnetic, whereas both positive and negative potentials are possible in electric and magnetic fields. So gravity, that the whole thing that I said right now is verbatim being repeated in this page. Okay, so gravitational potential are always negative, whereas both positive and negative potentials are possible. Now, Akshay, what happens when does the gravitational field become zero? Does it ever go positive? Exactly, at an infinite distance from the source, from where the gravitational field is occurring, then we get to see zero. We get to see zero potential. So therefore, we can never have positive potential in the case of gravity, because Earth is a source of gravity. Earth is under a negative potential well. Okay, so if we have to pick up an object and basically move it upwards, if we have to pick up an object and move it upwards, we have to feel the effects of gravity. And if we leave it, what happens? The object always falls down. That's why I call it a gravity well. Okay, so okay, our magnetic monopoles are thought not to occur. So true point source are only possible in electric and gravitational fields. Now, what is the meaning of a monopole? Okay, a monopole is a pole where you only have one polarity. There is no other polarity. Like in the case of magnets, we have two polarities, right? We have the north and the south. But if we try to break the magnet again and again and again, we will always end up with two poles. Okay, so in the case of magnetic fields, there is never going to be a unified pole. Okay, a unitary pole. Like you cannot have an isolated north pole or you cannot have an isolated south pole. So monopoles do not exist, at least for now. People are still under the, like they're trying to figure out if monopoles exist or not, but still now monopoles have do not exist. But we can have mono charges. Like you can have an isolated positive charge which will basically release electric fields in all direction, and you can have an isolated negative charge where all the electric fields are gonna go inside. Okay, so that does exist. So topic D1 and D2 give a description of the field in terms of a common set of concepts. There is no attempt to explain the gravitational or electrostatic force arise. How they arise, nobody cares. Nobody cares why it is happening in the first place. We just want to know the mechanics behind it. If we can understand the mechanics behind it, we can take use of it. Right? We can take use of it. To show this distinction, gravitational forces can be explained in Einstein's general relativity as a distortion of space-time by the mass of the attracting object. This leads to an inverse square law, and it is at this point that our theory begins. The assumption of inverse square behavior of electric and gravitational field is a useful algebraic description, but by no means the whole story. Now, the electric field strength. Now, you know what the same what do you say, a similar theory, a similar concept in gravity is the gravitational field strength is also known as acceleration due to gravity. The same thing happens here also. The electric field strength. The definition of an electric field strength arises from the thought experiment involving the measurement of forces acting on a test object. The test object is going to have very low charge. It is going to have very low charge. There is a problem in carrying out the measurements of field strength practically. The presence of test charge will distort and alter the field in which it is placed, since the test charge also carries its own field. So basically, what happens here? See, in the case of gravitational field, also what happened when we were trying to find the gravitational field strength of a particular object, we had to do it by bringing another object to that field. But if you bring another object to that field, what will happen? That object will create its own gravitational fields, thus distorting the gravitational fields of the original object that we are going to study. Right? The same logic applies here also. If you want to figure out what the electric field strength is of a charged particle, you have to use a test charge. But when you bring the test charge to that point, what happens? The test charge produces its own electric field, due to which what happens? The electric field that it produced distorts with the electric field of the original charge. Clear? Okay, so the definition of electric or field strength in general is force acting on an object or on a test object upon the size of the test object, as on page 476. It leads directly for electric charge to E is equal to force acting on a positive test charge upon altitude of the test charge. Understood? So what can we say? E is equal to F upon Q. So what was the formula for F given to us by Coulomb? What did Coulomb say? Coulomb said that force is equal to K Q Q dash upon R square. Let us, for the purpose of our explanation, consider that Q be the actual charge which is producing the field and Q dash be a test charge. Okay, so by definition, electric field strength should be equal to the force of the force that is existing between our charge and the test charge upon the charge of the test charge. So by this logic, we should say that E is equal to K Q Q dash upon R square the whole upon Q dash. Look at this, look at this. If the logic is breaking, please let me know. Is the logic safe here? We know that by definition, the electric field strength is force upon test charge. What is the force? The force is the electric force that is existing between the charge that we are keeping under observation and the test charge. Okay, now q dash upon r square is the force that exists between our charge and the test charge. So to find the electric field strength of our charge, what do we have to do? We have to divide the force by the test charge. So what do we end up getting? K q dash upon r square dot q dash. So this will end up being what? K q upon r square. This is the formula for what? This is the formula for electric field. Understood? This is the formula for the electric field. Now, the electric field is what? The electric field, how did we get the formula for electric field? Force divided by charge. Force divided by charge. Force is newtons, charge is coulombs, newtons per coulomb. So electric field, SI unit of electric field becomes what? Newtons per coulomb. Okay, is equal to newtons per coulomb becomes the SI unit. If you understood this, we can go back here. Let's see. Look at this. So electric field is equal to what? Force upon the charge of the test charge, where Q is the size of the test charge. The unit of electric field is newtons per coulomb. The definition of electric field strength, the point is that the force per unit charge, the force per unit charge experienced by a small positive charge placed anywhere around our charge, the main charge. It is the force per unit charge experienced by a charge placed in the electric field of the original charge. You can if your theory is clear, you can say it whichever way you want. Okay, by this book's logic, the definition of electric field strength at any point is that it is the force per unit charge experienced by a small positive point charge placed at that point. Okay, now, so basically, what is the electric field strength? For example, let us look at this. We have a charge Q in the center. Okay, so we have placed a point charge here. We have placed a point charge Q dash here. So basically, imagine for a moment you remove this q dash. Imagine for a moment you remove this q dash. Now if we remove this q dash, what ends up happening? What is the force that is going to be exerted at this point by this charge? On any charge, it is the force per unit charge. It is the if you get the force per unit charge, you can multiply it with any charge to get your force. See, force per unit charge multiplied by charge. So basically, if I say the cost of a banana is 3 rupees per piece, 3 rupees per piece multiplied by 10 pieces becomes what? 30. So 3 rupees per piece, 4 per force upon force per unit charge. Force per unit charge at this particular point. Now remember, see, if you just erase this and say that okay, at this point, what is my there is a point A which is at a distance of r from our original charge. It is at a distance of r from our original charge. What is my force per unit charge going to be? What is my force per unit charge going to be for any charge? So why am I trying to specify this again and again and again? Force per unit charge multiplied by charge gives you the force. Okay, acceleration due to gravity multiplied by mass gives you the weight. Force, again force. So basically, it is the what is acceleration due to gravity? It is force per unit mass. Acceleration due to gravity is force per unit mass. Similarly, the electric field is force per unit charge. Understood? So the definition, the direction of the electric field is the same as the direction of the force acting on the positive charge. Okay, so if you have a positive charge, then the electric field will be going outwards. If you have a negative charge, the electric fields will be going inwards, inside the charge. Clear? Okay, so the electric field strength is a vector quantity. It has the same direction as the force F because the charge is scalar. Exact extra attention to direction is required while electric field becomes because of two signs of charge. So electric field due direction. Electric field's direction has to be taken into consideration every single time we try to find the direction of a certain field produced by a certain charge. Okay, so let's go. Electric field strength due to a point charge. Okay, the same thing that we described here, kq upon r square, that's what we are going to do, but of a point charge. Imagine an isolated charge of size q sitting in space. What are the strength of the electric field at a point P, a distance r away from the isolated charge? We can use the positive test charge of size qt, and qt means the test charge. Okay, and at P and measure the force F that acts on the test charge. Okay, due to the isolated charge. Then the magnitude of the electric field F acting on the test charge becomes equal to what? K Q. Q is the charge of our own system, and then Q of T is the test charge upon R square. The electric field strength at that point is given as what? Force upon charge. So what do? You divide your test charge from your original force formula and you will get kq upon r square. Okay, so the electric field strength E at a distance r from an isolated point charge q is given as kq upon r square. It is given as kq upon r squared. Clear? Next, now worked example number 4. An oxygen nucleus has a charge of plus 8 electrons. Calculate the electric field strength at a distance of 0.68 nanometers from the nucleus. It is an easy problem. So we just have to say K Q upon R square is equal to E, and we have to find the electric field, right? So what do? We say we know the value of K as 9 into 10 to the power of 9 multiplied by what is the charge? The charge inside the nucleus is plus 8 electron plus 8e, so that is 8 into 1.6 into 10 to the power minus 19 coulombs upon r square, that is 0.68 into 10 to the power minus 9 the whole square. Clear? Okay, this is how you solve the problem. Any doubts? Okay, next. Rest, I don't have to solve it because you can use the calculator to find the solution. Okay, next. Yeah, but see, Akshay, see, if you are in vacuum, why do you have to go through the whole solution again and again and again and break your head? You are always gonna get 8.99 into 10 to the power minus, sorry, 10 to the power 9. I'm going to say 8.99 is 9 enough. It's good enough for me. 8.99 could be considered as 9, good enough for me. So why should I always break my head? So they are using permittivity. Now, when does this change? This changes when the medium itself changes. For now, all the medium is vacuum. That is why we are happy with epsilon naught. But as soon as the medium changes, what am I going to do? I'm going to put the appropriate formula and find the answer. Okay, now calculate the electric field strength in vacuum. So 1.5 centimeters from a plus 10 microcoulomb charge. Okay, so what is happening here? Now, see, this logic is going to be the same. You're going to use kq upon r square, but the only answer that's going to be different is whether it is going towards the charge or away from the charge. So in our case, what is happening? We are having a plus 10 microcoulomb. So a plus 10 microcoulomb is a positive charge. So the electric field will originate from the charge and move away from the charge. Okay, but and similarly, what will happen for a negative charge? The electric field lines will be basically going towards inside the charge. Rest everything is the same. Clear? Okay. Next, a nucleus of gold has a charge of plus 79 electrons and a radius of about 7 femtometer. Calculates the electric field strength at a distance of 1.5 nuclear radii from the center of the gold nucleus. So we know the charge, we know the radius. Okay, we know the charge, we know the radius. Calculate the electric field strength at about 1.5 nuclear radii. 1.5 nuclear radii, you know how much it will be? 7 multiplied by 1.5 multiplied by femto. Femto is how much, Akshay? Femto is how much? Milli, micro, milli, micro, nano, pico, femto. So how much will it be? Confident as well. Say with confidence. It is 15, 10 to the power minus 15, right? Yeah. So Fem2 is 10 to the power minus 15. So again, I'm going to repeat. So you have the milli, micro, nano, pico, and femto. So femto is minus 15. And in between, you have a small quantity called angstrom, which is 10 to the power minus 10. We use angstrom to basically describe the radii of all the atoms. Okay, all the atoms have the radii in the angstrom region. Clear? Okay, now calculate the electric field strength at a distance of 1.5 nuclear radii from the center of the gold nucleus. You can do this, right? No problem. Just feed the information in that kq upon r square and you will get the result. Clear? Okay, next. Akshay, you do this as homework. Okay, I'm gonna basically, if I think you can do it, I'm gonna give it to you as homework. Okay, if I think it will be, see, it's a direct formula based problem, right? So you shouldn't have a problem with it. Okay, so a free proton is at a distance of 1.5 nuclear radii from the center of a gold nucleus. Calculate the magnitude of the electric field of that proton. Now, Akshay, I want you to basically link electric field, this concept of electric field with the gravitational field. When the mass was given and they asked you to find the weight, what did you do? You multiplied it with acceleration due to, sorry, gravity, right? So here also, if the charge is given and then they are asking you what the force will be, then the force will become equal to how much? Q into electric field. See, if I give you the cost of one banana and ask you how much will cost for 10 bananas, what do? Cost of one banana multiplied by 10. Similarly, the force per unit charge multiplied by the charge will give us the force. Force per unit charge, which is the electric field, multiplied by the charge gives us the electric field at that point. Clear? Okay. The magnitude of an electric field at a distance of 0.25 meters from a point charge is 470 newtons per coulomb. The field is directed towards the point charge. So, Akshay, from this small line, the field is directed towards the point charge. What do you know? What can you tell me about the nature of the charge? Towards the point charge. It is negative. Exactly. Exactly. The field is directed towards the point charge. Calculate the value of the point charge, including the sign. So this one small line towards the point charge gave us the clue that the field is going towards inside the charge. Understood? Now, basically, we know that what? We know the value of, find the value of the point charge. Okay. Electric field is given as what? K q upon r square. So q will be equal to what? E multiplied by r square upon k, and a minus sign because it is going inside towards. This is the answer. Okay, you can solve it. Show it to me. Just I'll make this an assignment for you. Just upload it in the website. Calculate the distance. See, why am I asking you to do that? Because this will force this will give you a mental this thing that you have homework. So homework has to be done. Okay, do these homeworks, submit to me in a timely manner. Okay, so calculate the distance from the point charge plus 2.4 into 10 raised to the power minus 8 coulombs, at which the electric field strength is 1.0 into 10 to the power 2 newtons per coulomb. So here they have given us the electric field. Here they have also given us the charge, and all they are asking us to find is Q. Sorry, R. So what can we say? We can say that R square is equal to K Q upon E. and R is equal to root under K Q upon E. Clear? So they gave us the charge, they gave us the electric field, and then they are asking us to find the distance between the point and the charge. Easy. Clear? Next. So adding electric fields. Now, till now, we were talking about an isolated electric field, right? Now we have to consider what if more than a few charges are existing in the same place, and you want to find the electric field at a particular point due to all these fields. Okay, now here comes the vector addition. You have to consider the vector addition. Clear? Okay, so when there is more than one charge, the strength of an electric field. So I'll just explain it to you a little bit in a free form manner. So you have one charge q1 here, one charge q2 here. Okay, imagine you only had q1 and this was a point p. Okay, so if you only had q1, there will be a force. Like if this is positive and this is positive, let us imagine that the test charge that we are taking is also positive. So what will this positive charge q do? It will basically try to push this charge away if you only had q1. Now if you have only q2, okay, now imagine I'm just going to draw it with a different color. If you only had q2, what would happen? This is also positive. This would try to push this whatever charge you have here towards this direction, right? And the original one will try to basically push it towards this direction. So now there are two different forces existing on the same particle, right? There are two different forces or two different electric fields acting on the same point. So basically you have to have, and both of them have direction also. Both of them are producing an electric field at that particular point, and both of them have their own direction. So when such a scenario happens, what do? You basically take the vector addition. You cannot add them using scalar method. You have to add them vectorially. You have to know by what angles are these two fields aligning themselves. What is the angle between these two? Okay, so we have to understand that, and that's what we're going to do in this section. Okay, so we will have to be basically really, really strong in our vector analysis. So when there is more than one charge, the strength of an electric field due to two or more components must be found by vector addition. This means using either a calculation or a scalar diagram. Okay, a scale diagram. Vector addition is discussed in page 340. Now, figure 9a shows a positive test charge that lies on the line between the two charges of size q1 and minus q, plus q and minus q. The force on the positive test charge due to plus q is to the right. Okay, let me see the diagram first. Okay, see, look at this. Now you have a positive charge q here, you have a negative charge minus q here, and here is a small test charge, a positive test charge. Okay, so the positive test charge is feeling an outward push. It is feeling an outward push due to this positive q. It is also feeling an inward attraction. So someone is trying to kick you from one side, and the other one is trying to come basically grab you and hug you from the other side. So what happens here? The resultant electric field would be in this direction, right? So the particle will be moving in this direction. So this is what's happening here. We have to understand how to resolve such type of questions. Okay, the force on the positive test charge due to plus q is to the right. The electric field also produces a force on the test charge to the right. So the field is also to the right, the force is also to the right. Okay, now these now is due to the right, produced on the test charge to the right due to the minus q. Okay, so both of them, the positive test charge q is also producing a field to the right, the negative test charge q is also producing a field to the right. The positive test charge is also producing a force to the right, the negative test charge is also producing a force to the right. Both of them are on the right. Now, these two forces are drawn as vectors that act in the same direction. They act in the same direction. They are shown apart for clarity in this figure. They add to give a resultant force, and therefore a resultant electric field is shown. So you end up having a resultant electric field due to both of them. Clear? Okay, field due to plus q, and this is basically going to be the net electric field. Okay, next. Figure 9b shows an arrangement where the situation is no longer collinear. What is the meaning of collinear? When all the points are lying on the same line. When all the points are lying on the same line. What is coplanar? Co means same. Co means same. Planar means what? Same plane. Co-linear means what? Co means same. Linear means line. Same line. Co-linear, same line. Co-planar, same plane. Okay. Now, figure 9b shows an arrangement where the situation is no longer collinear. The charges and the test charge do not lie in the straight line. There are three charges. Charges 1 and 2 have a charge of plus q, while the third charge has a charge of plus 2q, but is much closer to the position of the test charge. Again, either a scale diagram or a calculation works. The length representing the forces acting on the test charge due to plus 2q is much greater than the other two, which leads to a final summed field that is shown downwards. Now let us look at this. What is happening here in the second case? See, there are two charges here. There is a charge plus q, and there is another charge plus 2q. Okay, so this is the test charge. Now, the plus q charge is feeling the effects. This test charge is feeling a force in is feeling a force in this direction. It is feeling a force in this direction. It is also feeling a force in this direction. Okay, but this plus 2q charge is much closer to this test charge. So what ends up happening? This plus 2q charge is able to push this test charge downwards. So what happens? You get the resultant field downwards. Understood? You get the resultant field downwards. Now, Akshay, I will try to explain this to you by resolving these vectors in the horizontal and vertical direction. Okay, so you have a plus q charge here, you have a plus q charge here. Okay, sorry, plus capital Q charge here, and you have a plus 2q charge here. Okay, and this is the point of the test charge. So basically, we are getting a line like this. We are getting a line like, oh my god, we are getting a line like this, a line like this, and a line like this. Clear? Now, can I, at this point, I can basically resolve this this force. Okay, this force into this and this, right? This one. Similarly, I can resolve the other force in this and this direction, this one, right? Okay, and the third one is basically in the plane itself. Now, basically, this q and this q are the same magnitude, so their horizontal component of forces will also be equal in magnitude. So basically, they cancel each other out. So basically, you have two forces, that is q, the vertical component of these two forces add up, and then they are the ones challenging the force due to the plus 2q, and that is what's being represented here. Look at this. See, their net force is upwards, and the plus 2q charge net force is downwards. Their electric field is upwards, and the plus 2q charge electric field is downwards. Now, all we have to know is whether they beat them or not. They don't. Okay. So the resultant field will be net downwards. See, look at this. Basically, look at the vector's length. A vector's length represents its magnitude, right? A vector's length represents its magnitude. So basically, if the net force is here by due to these two charges, it is not that long. I'm sorry, but you're not that strong. Okay, but the contender that is going downwards is big. It's huge, right? Therefore, what happens? You get a net electric field in the downward direction. Did you understand what was happening here clearly? Now, if we use angles and all, I basically didn't want to use angles at all because I wanted to make it very simple that we have one horizontal component, we have one vertical component, that's it. Whether where you place the theta, you will get your different values, cos theta, sin theta, and all of that stuff. Okay, we are going to understand this more in this one question. Now, 2 point charges of plus 25 nanocoulomb charge X and plus 25 nanocoulomb charge Y. Okay, these two are the two plus 25 nanocoulombs. Okay, now are separated by a distance of 5 meters. Calculate the resultant electric field strength at the midpoint between these two charges. Okay, this is the point they are asking us to find the midpoint. Now think about this, Akshay. Think about this. If we consider the test charge to be of let's say the positive. This is positive. This is positive. This is positive. Okay, I'll write it down. Positive, positive, positive. Okay. Now I'm going to transport to you a different example. There is a table in the middle. Okay. Now I am trying to push the table with a force of 50 newtons towards the right. You are trying to push the table with a force of 50 newtons towards the left. Okay, both of them are putting a force on this midpoint, right? Both of us are putting a force on the midpoint. But does the table bulge even a little bit? No, right? It does not move at all. Why? Because we were putting the same force. Correct? We were putting the same force. Now look at this. Both of them have the same charge. Oh my god. Oh my, I'm so sorry. I in my haste I read them as both plus 25. So this is plus 25 and this is plus 15. I'm so sorry about that. Okay, I thought they were both plus 25. They are separated by a distance of 0.5. Now, Akshay, in the middle, what is going to happen? Let's see. The electric field, sorry, in the middle, right? Exactly in the middle. So this distance will become 0.25. This distance will become 0.25. Both the distance are 0.25, right? Okay. Now what's happening? Now 0.25, 0.25. Now this is plus 25 and this is plus 15. So basically here the electric field is going to be in this direction, and here the electric field is going to be in this direction. Now let us check the magnitude. One will be kq upon r squared kqx. I'm just going to write x because it's this point, kqx upon r squared, and the other one is going to be kqy upon r squared. Okay, so basically if we compare them both, we know that this x component wins, right? Because it has a higher magnitude and the distances are the same, so the x component will have a higher magnitude. So I can directly say the resultant will be equal to what? So basically if you are pushing this from this side with a force of 20 newtons and I am pushing this side with a force of 10 newtons, the resultant will be 20 minus 10 in this direction, 10 newtons in this direction, right? So this will become equal to k upon r square. I can simply take it out and I can write qx minus qy. So is equal to, they have asked us to find the field only, right? They have only asked us to find the field, not the force. Okay, yeah, field is fine. So this will become equal to 9 into 10 to the power of 9 upon 0.25 the whole square multiplied by 25 minus 15 into 10 to the power nano or micro? Nano, 10 to the power minus 9. Clear? So this and this can get cut off, and you will be left with 9 into 10 upon 25 square is 0.25. So I can write it as 25 upon 100 multiplied by 25 upon 100. So I'll be left with 9 into 10 to the power 9 into 10. Sorry, I'll just write it as 90. 90 upon uh, 25 into 25 into 100 into 100. 25 fours are 100, 25 fours are 100, 9 16 4 fours are 16, 16 nines are 144, 1440. Is it correct? 1440 newtons per coulomb, right? So I kept them all the same so that I didn't have the need to use a calculator. See what I did, you understood, right? So basically, you understood? Okay, fine. Next, many a times you will have to use these methods so that you can save time. Now, calculate the distance from x at which the electric field strength is 0. Okay, so Akshay, all you have to do is basically make sure that this thing kq upon rk qx minus qy upon r square should be equal to 0. Understood? So basically here, like at some point in the r square region, the whole thing will become equal to 0. Okay. Hmm. No, wait, hold on. Kq upon r square should be equal to minus kqx upon r square should be equal to minus kqy upon r squared, because one is in this direction, the other is in this direction. So basically both of them should be equal to same, then only this will happen. So no, again somewhere I'm making a glitch. One second, hold on. Yeah, they have it. Yeah, this is Akshay Tapare. Same thing they have written. E of x should be equal to minus E of y. I'm right. E of x should be equal to minus E of y. So these two things should be equal. Okay. So let's. Yeah. They cannot have the same. Okay. I'll explain it to you what is happening here. So basically, you have this is x and this is y, and you are saying let this be a random point. Uh, this whole thing is how much? This whole thing is 0.5 meters. Okay. So you are saying let this be this distance be a, and this distance will be equal to 0.5 minus a, right? So you are saying that these two should be equal. Okay, so now it's correct. Now I'm the right path. So you can say that e of x should be equal to e of y minus e of y at this particular point. So this electric field should be equal to this electric field. Why have I written minus? Because E of y is in this direction. Okay. If E of x is in this direction, E of y is in this direction. So E of x can never be equal to E of y ever. But E of x, this E of y, this is E of y, right? Minus E of y will be here. Minus E of y. So E of x should be equal to minus E of y. The directions are the same. Do you understand why the logic happens here? Why you have to use minus? Because E of x and E of y, even if they have the same magnitude, will never be the same because by nature their directions are different. By nature their directions are different. Am I right? See, Akshay, what I'm tell you is, you see that's what's going to happen, right? If both of them are going to be equal, at the end of the day you have to do that only. You have to do what? You have to say that basically k q of x upon a square should be equal to k q of y upon 0.5 minus a the whole square. That's what we are going to do at the end of the day. Yes, we are going to do that only. Okay, so basically the k gets cut off. Okay, let's fill in the values. So 25 multiplied by 10 to the power minus 9 should be equal to 15 multiplied by 10 to the power of minus 9. Okay, upon, and this should be upon a square, and this should be upon 0.5 minus a the whole square. This and this gets cut off. This is 5, 3 the 15, this is 5, 5 the 25. So you will have um, 5 into 0.5 minus a the whole square should be equal to 3a squared. So basically 5 into 0.5 the whole square is 0.25 plus a squared minus 0.5 into 2 is 1 minus a is equal to 3a squared. Okay, now I'm going to multiply this. 25 into 5 are 125. That is 1.25 plus 5a squared minus 5a should be equal to 3a squared. You bring this here. What happens? So 5a squared minus 3a squared is 2a squared minus 1.25, sorry, plus 1.25 minus 5a should be equal to 0. Okay, first things first, I'm going to break the curse. What I'm going to do is 2a square minus 5a plus 1.25 is equal to 0. Okay, should I just use the quadratic formula? Yeah, you can do it. You can do it. You try to do it. Yeah. 2a square minus 5a plus 1.25 is equal to 0. Therefore, how? You can then directly put this in the calculator, right? Okay. What is the answer? These are is a- Oh, I always forget the other method. The other method is super cool. Just give me 1 second. The negative d, you just ignore it. 0 point? 0.28. Yeah, 0.28. That's the correct answer. Yeah, 0.28. Yeah, correct. Okay. So next. Now, finally, did you understand this logic? Okay, let's move on. So we have to find the magnitude of the electric field at the point P on the diagram. Okay. So at this point P, what is happening here? They haven't given us any angles, right? Oh yeah, they have given us the angle. This is 90 degrees because 3, 4, and 5 Drupad. Sorry, 3, 4, and 5 Akshay. It's a right angle triangle. Okay. So Huh. If I try, I'm just gonna redraw this. Okay, I will just redraw this like this. Okay, X, Y, and this is the P. You have 0.5 meters, 0.4 meters, and 0.3 meters. Okay, and this is XY and this P. Okay, so 0.4, 0.5, and 0.3. Okay, fine. Huh. So I can say that due to this, at the point P, electric field is like this, and for this, the electric field here is like this. Okay. Mm. So the angle has to be, if these two are straight angles, Akshay, these two angles also has to be 90 degrees, right? Because they are vertically opposite to each other. So if they're vertically opposite to each other and you have two vectors, the sum of the two vectors becomes equal to what? We know that sum of two vectors is what? X squared plus y squared plus 2xy cos theta. This whole thing becomes zero because of the 90 degrees. So you only end up being root under x squared plus y squared. Okay, so all you have to find is the electric field from X at this point. You have to find the electric field from here at this point. Okay, and then we find the root. Okay, let's do this. We know that this is how much? 25 nano coulombs. This is 15 nano coulombs, like 25 and 15, right? Or is it 2.5 or 1.5? Okay. Okay, so Ex becomes equal to how much? Ex becomes equals to k uh, yeah, better, k q of x upon r of x the whole square is equal to k 25 into 10 to the power of minus 9 upon 0.4 the whole squared. Okay, and e of y is equal to kq of y upon r of y the whole square is equal to k multiplied by 15 into 10 to the power of minus 9 upon 0.3 the whole square. Yeah, I figured it out. Now, you find the values, you put the value of k as 9 into 10 raised to power 9. So, what do you get? So, 9 into 10 to the power of 9 into 25 into 10 to the power of minus 9 upon, we get 4 4 the 16 into 100 into 100. How much? Something like that. Yeah, that is correct. Okay. And the other one, EY becomes equal to what? 1500. So this becomes equal to 1400 and this becomes 1400. Okay. Yeah, fine. So, and this is equal to 1500. So, basically, root under 1400 the whole squared plus 1500 the whole squared becomes equal to how much? Um, how much? 2100. Okay, clear. So, 2100 newtons per coulomb should be the answer. Okay. Now, the calculation of the angles was not required in the question, and it is left for the readers. Okay, and it is left for the readers by because the angle between them is how much? 90 degrees. Okay, the angle between them is 90 degrees. Okay, now Akshay, if you want to figure out the angle, then what do you do? You say that what நீ சொல்லு, what do you take, what do you do? Okay, so let's call this to be theta. Okay, if this is theta, then this is E of x and this is E of y. Can I transport this E of y to here? Why? Because these two are what? These two are parallel, their direction is the same and their magnitude is the same. So, can I say, Akshay, tan theta is equal to E of y upon E of x? So, theta is equal to tan inverse E of y upon E of x. That will be the answer. Okay, this will be the angle, and you will say that this resultant vector is making an angle of this much with the ex axis. Clear? Okay, next. Okay, so was this the only question in this page? Yeah, okay, fine. Yeah, okay, fine. Yeah, it's fine. Just hold on one second. Okay, so we are going to conclude the video for this class today here. Okay, and for tomorrow, we'll continue with the questions and the electric field lines. I hope you really enjoyed my video. I make my explanations really, really easy, and anyone who is watching my video can follow me. If you have any doubts, please comment below, and I'll try to answer them as fast as possible. Okay, if you like my video, please like, share, and subscribe my channel. I am Rama, and this is Rama Teaches You, and see you on the next video.